Welcome to paper 3 for Mechanics 2023. Let's just get started. We've got question 1. Ooh, is it gone? Okay, a car is initially at rest on a straight horizontal road. The car then accelerates along the road with a constant acceleration of 3.2 meters per second squared. If you ever see constant acceleration, this is probably going to be a SUVAT type of question. Okay, so whenever I see constant acceleration, the first thing what I like to write down is just SUVAT on the side, and I'm going to try to fill in some numbers. Sometimes this can be a time graph question, which it might be better to do. I'm going to keep on reading on, but let's have a look. Find part A, the speed of the car after 5 seconds. Okay, so maybe you can make a speed time graph. Sometimes in those situations it's better to do. In this case, I'm going to stick with SUVAT. So the question is asking the speed of the car, so I'm trying to work out V. At the moment, or at the start, it was at rest, so that means my U is going to be 0. My S, how far has it traveled? I don't really care about right now, just for part A. I do have a constant acceleration, which is 3.2, and I also have a time, which is 5. So I have these 4 letters. Any 4 letters you can use to work out one of your SUVATs. We have a couple of SUVAT equations that I'm actually going to bring up on screen. These are all in your formula book, so you don't actually need to learn them, but as you can see, every single one of these equations only has 4 letters in them. So in this case, we have V, U, A, and T, so I can just use this first equation here. So that means that using V equals U plus AT, that means that V, which is what we're trying to work out right now, my U is 0, so 0 plus 3.2 times by 5. If we put that into a calculator or work it out like so, this gives us 8. No, it doesn't. It gives us 16. Don't know why I said 8. It's 16 meters per second. I should probably get my calculator up as well. Okay, part B says find the distance traveled by the car in the first 5 seconds. Okay, so now we're trying to work out S. Try to avoid using stuff that you've already worked out. So for example, you've worked out V is equal to 16. Try to avoid using that V. Try to use the stuff that's already given to you in the question. That way, just in case you have made a mistake, that error isn't carried through and you still end up with full marks for part B. Okay, so this time we have S, U, A, and T. So we're going to be using this equation here. S equals UT plus a half AT squared. UT, that's just going to be just 0 because U is 0. A half times by 3.2 times by 5 squared. And we can put that into our calculator. A half times by 3.2 times by 5 squared. 40 meters. If we were to do this with the velocity time graph, I'll show you how we would do this with that. So you can see we start from rest, and then we also have a constant acceleration. So the speed, the graph is essentially just going up like this. This is the velocity, this is the time. Okay, and we're just trying to work out this here. What would be the speed here if our acceleration is 3.2? Again, it's very, very similar. Kind of we follow the same rule with this. So that just has to be 5 times by 3.2 to work out your new velocity here. Okay, and then the area underneath this graph would be your triangle, which is a half times by your time. And then the area underneath this graph is going to be your distance traveled essentially. So if we worked out the velocity here was 16, this would just be a half times by 16 times by 5, and I believe that should still give us the same answer. A half times by 16 times by 5. As you can see, it still gives us 40. So it doesn't really matter which method you use. Either way is fine. In some cases, it might be just better to use this. Question 2. We've got particle P with mass 5 kilograms, and it's being pulled along a rough horizontal plane. So as I'm reading this, I'm going to try to annotate the diagram. So this is rough, and we also have a mass of 5 kilograms. I'm also just going to annotate the downwards force, which is going to be 5G. Cool. The only resistance to motion is a frictional force going left, this F, as shown in figure 1. Find the magnitude of the normal reaction of the plane on P. That's pretty simple. the reaction force will equal to the downwards force. Okay, up is equal to your downwards forces. Okay, at the moment our only downwards force is 5g, so that means your reaction force upwards, that also has to be 5g. But because it says magnitude, we should probably work out what g is. In our calculator, we can just do 5 times by 9.8. That gives you 49. Okay, I actually do have g stored as a 9.8, and this just makes my calculations a lot more quicker to do sometimes, like so. And if you are curious, because this is CG50, but same with your other calculator, you can store some numbers. I'll show you how to store it in this, but it's very, very simple. In the other one, there should be a button that just says store on your I believe it's a 991EX off the top of my head. So what you're going to do on the CG50, you're gonna click Shift. Then you're going to click, you're going to type in the relevant numbers. So for example, if you want to store like 9.8, okay, then you're going to click this arrow, and then you're going to click whatever letter. So click alpha first, and alpha G, because I use G for gravity, equals, and then type in alpha G, and you can see G is equal to 9.8. Okay, this works for anything, and it's slightly different. Just watch a YouTube video for the relevant calculator that you have. Okay, and for part A, it's just going to be 49 newtons. So part B, the particle is accelerating along the plane at 1.4 meters per second squared, and it's asking us to find out the value of friction. So the way that friction works is you have two types really. One is your maximum friction, okay, so that's called Fmax. And the other way is when you just have friction opposing in the opposite direction. So, for example, let's say our Fmax for a different particle. Let's say our Fmax is 10 newtons, right? Now, if we apply a force of 12 newtons to the right and 10 newtons to the left, well, the particle will move at a resultant force of 2 newtons to the right. Cool. Now, using the same idea, if I pull 2 newtons to the right, well, actually, I will not have 10 newtons to the left. Nope. I will only have 2 newtons to the left because of my frictional force, because of the flow. But how far it can go up to, so even if it's, let's say, 6 newtons on the right, it will still be 6 newtons on the left. But our limit, essentially, is up to 10 newtons. And as soon as it hits 10 newtons, we will call this at equilibrium. And any point above that 10 newtons, any point above that Fmax value, then we say, okay, now we're going to start to move by a resultant force of 1 newtons, by a resultant force of 2 newtons on the top. Okay, that's how your friction works. So that's actually very, very similar to kind of what's going on here, and that's why we have an acceleration of 1.4. So if you ever have an acceleration in a forces question, you're just going to use F equals to ma. So this is going to be force, our resultant force, you're going to use right minus left. So we're going to have 28 minus F. That's our resultant force. I'm going to put Fr for friction. My mass is equal to 5 and my acceleration is equal to 1.4. If I do 5 times by 1.4, that gives me 7 newtons. So that means 28 minus your friction is equal to 7 newtons. And friction must then equal to 21 newtons. Perfect. So then part C, the coefficient of friction between P and the plane is mu. Find the value of mu. So we've got friction, we've got our reaction force, and the formula for friction, or Fmax really, is mu r. Therefore, if we know friction is 21, r is equal to 5g. Therefore, mu must equal to 21 divided by 5g. Let me write that down here, which is going to be 3/7. And that's going to be our final answer. Let's say, oh, it's a two significant figures. Let's convert that. 0.43. There we go. That's our final answer. Very nice. Question 3. At time t seconds, where t is bigger than or equal to 0, a particle p has velocity v meters per second, where v is equal to that. Okay, so just by looking at this type of question, it looks like a variable acceleration question. All right. Now, part A is asking us the speed of p at time equals 0. So speed, first of all, is a it's not a scalar value. Sorry, it's not. So speed is a scalar value, not a vector value. Okay, so what it has, it doesn't really matter which direction it's going into. It doesn't matter if it's going left or going right, you're always going to have a positive speed. So at time equals 0, we're just going to sub t equals 0 into here. What happens is all your t is set to 0, so we end up with 7i minus 3j. But since we want a speed, this is still velocity, we don't care about the direction. The speed is going to be the magnitude of 7i minus 3j, which is essentially 7 squared plus minus 3 squared. Doesn't really matter about the minus of this because minus 3 squared and 3 squared are the same thing. They both go to 9. But if we put this into our calculator, the square root of 7 squared, and I'm just going to put 3 squared because I'm lazy to type the minus. But in this case, I'd say, you know what, let's do it. Minus, they still give us the same answer though. Make sure you put in the brackets around the minus 3, otherwise you'll get a different answer. And you get root 58. Root 58 meters per second. If you want to convert to decimals, you can, but this should be fine. So part B, it says the value of t when moving p is moving parallel is part B. The value of t when p is moving is parallel to I plus j. So essentially that means that your speed is like I plus j meters per second, or 10i plus 10j meters per second, maybe 25i plus 25 plus 25j. You get the idea, okay? The i's and j components are the same. So we can actually abbreviate this as lambda I plus j meters per second. Okay, so that's our velocity of this. So essentially we're saying that 2t squared minus 3t plus 7i plus 2t squared minus 3, I think it said. Let me just double check. Yeah, this is our original speed, is equal to lambda I plus j meters per second. Cool, don't really need the meters per second. I'm just going to put that on the side a little bit there. I'm going to expand out this right hand side, so I end up with lambda I plus lambda j. And now what we can do is start to compare the coefficients. So you can see that if these two coefficients are the same, lambda lambda, that means that these two must also equal. So that means therefore t squared minus 3t plus 7 must equal to 2t squared minus 3. And now this is a quadratic. You can begin to solve. If I move everything to one side, I end up with t squared plus 3t. If I minus 7 from both sides, I end up with minus 10 is equal to 0. Okay, so I'm just moving all the terms to one side and equaling it to 0. And then I'm going to go into my calculator. Let's just solve it. So that's going to be 1, 3, minus 10. And you end up with two values of t, which I'm going to pretend to factorize like so. Therefore, t is equal to 2 and t is equal to minus 5. Can't have a negative value of t, therefore t must only equal to 2. Perfect. Part C, the acceleration of p at time t seconds. So if our velocity, I'm going to take a screenshot of the original question. Like so. So if our velocity is this, and we want to work out acceleration, there are a couple of things you need to know. When you differentiate when you differentiate distance or displacement, this gets differentiated to velocity, and velocity gets differentiated to acceleration. Okay, and then similarly backwards, velocity gets integrated to displacement, and acceleration gets integrated to velocity. Okay, so this order you really need to know. So to go to acceleration from velocity, essentially we're differentiating this. So we're going to differentiate the item first. So this goes to 2t minus 3i plus 4t j. I can write 4t like this. Okay, that's your acceleration term. Okay, and that was question C. Question D, it says the value of t when the direction of acceleration of p is perpendicular to I. So perpendicular to I, well, I is going to the right, right? Therefore, being perpendicular to it must be going up, which is essentially j. So essentially what it's saying is, at one point do you have the acceleration in part D when it has no I component. essentially when the coefficient of this is 0. Well, therefore, you can make an equation. You can say that the coefficient of I, which is 2t minus 3, is equal to 0. Therefore, t is equal to 3 over 2. Okay, and that's it. That's it for part D. Let's move to question 4. In this question, I and j are horizontal vectors. Cool. A particle P is moving on a smooth horizontal plane. A particle has constant acceleration. Okay. At time equals 0, it passes through the point A. Time equals 5, it passes through the point B. And the velocity of P is this. Find the speed. Okay, I see constant acceleration. I'm going to write down suvat. You can even draw a diagram if you really want to. Kind of where the points may be, like point A, let's say point A is here, point B is maybe here. Doesn't really matter. But we do know it has constant acceleration, so I'm going to write this down here, 2.4i plus j. Technically, this is going to be r equals, so because we're working in terms of vectors, it should be an r value, but we'll move. The velocity of p as it passes through A is this, so that means that at time equals 0, or the initial time, we're going to have this, minus 16i minus 3j. We're trying to work out the speed of p. So again, this is the magnitude of the velocity. The speed of p as it passes through B. Well, B we know is at t equals 5. Okay, so we're trying to work out v equals. Well, one of the equations we had from before was v equals u plus at. I'm going to use this equation. Don't really need any grid here. So we're going to be using v equals to minus 16i minus 3j. You want to use a full term, the i's and j's. Okay, plus, well, we're doing 5 times by acceleration, so we have 5 times by 2.4i plus j. You never, ever, ever want to use acceleration or any sort of vectors if you are squaring them. Okay, if you have a v squared, if you have a t squared, is fine because t squared is just a time, right? But if any point you are squaring your acceleration, squaring some sort of vectors, that's not going to work. Okay, and I'll show you how to do that potentially if it's in this question. But you will most likely be. I would like you guys to separate the x components out and the y components out. So you want to make 2 suvats in those cases. Okay. Anyways, let's continue to solve this part of the question. So what I'm going to do is expand out this here. So this becomes minus 16i minus 3j. 5 times by 2.4 is 12, I think. 5 times by 2.4 is 12. That's 12i plus 5j. We go ahead and simplify this. This becomes minus 4i plus 2j. But we do want the speed, so we're going to do some Pythagoras. 4 squared plus 2 squared. That's going to be root 20. I always like to check. I don't trust my mental maths. Yeah, 2 root 5 or root 20 meters per second. Alright, perfect. The point position vector of A is 44i minus 10j. Okay, and the position vector of C is this. We do have a constant acceleration. We do have, again, our initial speed. We need to work out the value of t. Okay, I'm going to make another suvat. I'm going to make this a bit more smaller. So, part B, let's make another suvat. Position vector is, we'll worry about that in a second, actually. Again, u is going to be minus 16i minus 3j. Acceleration is going to be 2.4i plus j. And we're trying to work out when does it reach 4i plus cj, or rather, instead, because it's displacement, we should kind of think about, well, what has happened from 44i to get to here. Okay, well, the I component, you've traveled minus 40i. Okay, we've gone down. Okay, and then what do we do from minus 10j to get to cj? Well, we can add 10j, and we can also add cj. Okay, so I'm going to combine them like so. Kind of just factorize it. Okay, you're kind of thinking the displacement. If this point is a starting point, okay, if that's the starting point, what are you doing from this vector? That should be highlighted, to be fair. What are you doing from this vector to get to the second vector? Okay, and well, what we're trying to work out the value of t. Okay, our equations from before. Let me scroll back up and then just copy them down. Here we go. Okay, well, we've got S, we've got U, we've got A and T. We're trying to work out S equals UT. We're probably going to be using this equation here, and this will be completely fine since we're not squaring any vectors. So S, which is going to be minus 40i plus 10 plus Cj, is equal to UT, which is going to be minus 16i minus 3j. Ooh, this might make a bit of an issue, but let's keep on going. Plus a half a, which is going to be 2.4 t squared, or even 2.4i plus j t squared. You can see this looks like a mess right now. Okay, and how are we supposed to solve quadratics? Because this is a quadratic here. How are we supposed to solve quadratics when we have an I component and when we have a j component? So what you can do instead actually is you can go ahead and separate the y components and the x components a bit. Okay, so what I'm going to do is actually make another suvat or two suvats, just focusing on the x components, or the I. I'm going to use them interchangeably, x and y and I and j's. When we're focusing on the I component separately and the j component separately. Okay, so this is my x component. So it's going to be minus 40i here, minus 16i, 2.4i, and my t states remains t. And I can do the same thing for this. This is going to be 10 plus c. This is going to be, even I can remove the i's here. Don't really necessarily need them. U is going to be minus 3, a is going to be 1, and t is still remain t. Perfect. Now what I can do is apply suvat on this, and then I can work out a value of t. So I'm going to do the same thing, use this equation here. Minus 40 is equal to minus 16t plus a half 2.4 t squared. Well, a half 2.4 is just 1.2. Now we can go ahead and rearrange this. Okay, this becomes 1.4 t squared minus 16t plus 40 is equal to 0. Now I'm going to put this into my calculator and go ahead and work out the value of t. And that gives us 1.2 minus 16, 40, and we get two values of t actually, where t is equal to 10 and t is equal to 3.33. Well, the question said that t was bigger than 5 actually, so we don't need this. That means the value of t is 10. Now what we can do, now we know the value of t is 10, we can apply the exact same thing, suvat on this, and work out the value of c. So that's going to be, we're going to do the same thing, use this equation again, s equals ut plus a half at squared. Okay, we're just essentially subbing everything into there. 10 plus c is equal to minus 3t, which is going to be minus 30, plus a half a, which is 1, t squared, which is going to be 10 squared. Okay, let's go ahead and rearrange for this. This gives you minus 30 plus 50 is equal to 10 plus c. You have to simplify that right hand side. 10 plus c is equal to 20. Therefore, c must equal to 10. And that's it. Perfect. And actually, we've done part B and part C at the same time, which is crazy. We worked out the value of t, which was 10, and we worked out the value of c as well, which was 10, and we got 4 marks for that, which is great. All right, let's move on. Question 5 here. A small ball is projected with speed 28 meters per second from a point O on a horizontal ground. After moving for t seconds, the ball passes through the point A. So the point A is here. Okay, and that's 20 meters above the ground. And this is 40 meters. Okay, cool. The motion of the ball from O to A is modeled of that. Okay, so this is a projectiles question. And there is one way that I like to do projectiles, and it works every single time. Okay, what you're going to do is going to make two suvats. Again, one for the x component and one for the y component. We want to show that t is equal to 10 7 cos alpha. Alright, just by doing this, you're actually going to set up some equations, which is going to help you more or less answer the whole question. Okay, first of all, let's look at the y components. And in fact, before you even start, let's actually separate this 20 meters per second into its x component and to its y component. So our y component is going to be this orange line, and this x component is going to be the green line. Whenever you have a hypotenuse and an angle, let's use some SOHCAHTOA. Right? If we have a hypotenuse of 28, well, this is the opposite side and this is the adjacent side, and this is a hypotenuse. To work out the opposite, when you have the hypotenuse, you're going to be using sine. Okay, so that means that sine alpha must equal to hypotenuse over, opposite over hypotenuse. Therefore, opposite over 28. Therefore, if we rearrange this, 28 sine alpha must equal to your opposite, like so. Similarly, we can go ahead and rearrange for alpha in the same way, and we find out this will be 28 cos alpha. Okay, that means our vertical component here is going to be 28 sine alpha, and horizontal component will be 28 cos alpha. Okay, and I'm going to use those as my u values for my x and y, so this is going to be 28 cos alpha, 28 sine alpha. Cool. We'll worry about the values of sine alpha and cos alpha later on when we can work it out. Alright, next bit, we know our distance potentially. Our v we don't know yet. Our acceleration we do know. Horizontal acceleration will be always 0, whereas the acceleration in your vertical is always going to be negative g. Alright, we got some information right at the beginning of the question of point A, right? We've got its horizontal distance and its vertical distance. So what I'm going to do is actually use that for our SUVAT, potentially for part A, and it might even help us with the next parts, which will be nice. Okay, alright. So if I use this value here, which is 40, okay, that will be at time t. But because it's reaching at point A, which also takes account of this 20, these two x and y are linked with the value of t. Okay, and that means this s component will be 20. Cool. I'm going to make a SUVAT with x and y. Okay, and again we have s, u, a, and t, so the equation we're going to be using is going to be s equals ut plus a half at squared. Alright, if I sub everything in, I get 40 is equal to ut, where that's going to be 28t cos alpha, okay, plus a half 0 t squared. Well, 0 is just 0, so we don't actually have that second bit. It doesn't really matter. Okay, I'm going to do the same thing for the right hand side. Let me get a bit more space. 20, so I'm just subbing everything into this equation again. But for the y component, 20 is equal to 28t sine alpha plus a half minus g t squared. I'm going to rearrange this as minus 4.9 because that's what a half times by negative g is anyways. So this will be minus 4.9 t squared. Alright, perfect. Well, now we have two quadratics. Well, part A is telling us to rearrange for t. Okay, so that means that I'm going to do 40 divided by 28 cos alpha, and that must equal to your time. And you can see this simplifies very, very nicely. We have a common factor of 4. So I'm going to do divide by 4 on the top, divide by 4 on the bottom. And that becomes 10 over 7 cos alpha must equal to time. Which is great. Alright, well that's part A done. But you can see because we have a value of time and these two are linked with the same value of t. I know you switch to capital T here, but it doesn't really matter. These are linked with the same value of t, so essentially what I can do is take this expression here and sub it into here, because then we are now linking our x and our y. And this is probably going to help us for part B as well. And that's the beauty of projectiles and mechanics. You can follow one method and it just works, and you don't even actually have to look at part B, C, and D. You can kind of just follow the method, and a lot of it is just you just getting marks. Right, so I'm going to put this equation into here. So this becomes essentially 20 is equal to 28 times by 10 over 7 cos alpha sine alpha minus 4.9 10 over 7 cos alpha all squared. Alright, let's go ahead and clean this up a bit. So this becomes 20 is equal to, well, before multiplying this out, I'm actually going to try to cancel out the denominator. So this is actually 28 over 7, which is the same thing as 4. 28 divided by 7 is 4. So this will be essentially 40 sine alpha over cos alpha. Okay, you can check that in your calculator if you're unsure. You can just focus on the number bits, but I'll show you anyways how you can do that. You can do 28 times by 10 over 7, and don't put anything that's algebraic, and you can see that still gives you 40. Okay, and then we bring in the sine as well, and we have to multiply by the sine alpha over cos alpha. You might already identify an identity here. Same thing on the next bit. It's going to give us 4.9. This bit might be a bit more trickier, so I'm actually just going to expand it out like this. 49 cos squared alpha. Okay, and then what I'm going to do is just put this into my calculator again. 4.9 times by 100 over 49. You can see there's a bit of a cancellation here, but let's just see what it simplifies to. It simplifies to 10. So this is going to be 20 is equal to 40. Well, let's stop here for a second. This is tan alpha minus we had 10 over cos squared alpha. Alright, the question's asking us about making an expression with tan squared. Well, at the moment we don't have tan squared, but we do have cos squared. How can we write cos squared when it's on a denominator? Well, we can write this as 20 is equal to 40 tan alpha minus 10 sec squared alpha. How is sec squared linked to tan? There's an identity. Using your sine squared plus cos squared is equal to one identity, you can actually make a new identity from this. Well, you can make tan squared plus 1 is equal to sec squared. So using this identity, I'm going to sub this into here. And I'm just going to quickly explain as well how I ended up with this. Divided by cos squared for each of the expressions. Okay, anyways, let's continue on. This gives us 20 is equal to 40 tan alpha minus 10 tan squared alpha plus 1. And continue to expand and clean up. And this becomes minus 10 squared alpha minus 10. And move everything to one side. And you can probably even divide by 10 now if you want to, but I'll do that at the end. 10 squared alpha, 10 tan squared alpha. Put the alpha there, sorry. 10 tan squared alpha minus 40 tan alpha plus 10 is equal to 0. Divide everything through by 10. Tan squared alpha minus 4 tan alpha plus 1 is equal. Ooh, I've done something wrong. That should be plus 30. That goes to plus 3. That looked a bit wrong. Yeah, just make sure you're moving everything to the side correctly. Essentially, I took away this. I added this. And I was supposed to add this, and I did fix that. So you're also supposed to add this. 20 plus 10 gives you 30, and you can see this simplifies like so. And you can always check with that, show that bit, which is great. All right. Well, not even necessarily reading on to part 3. You can part C. You can even continue on with this. Well, this is a quadratic. What I'm actually going to do is actually factorize this real quick, and you can use a u substitution real quick. Let's say u is equal to tan alpha. So you end up with u squared minus 4u plus 3. If it's a bit more easier to identify, and this ends up with, if you factorize this, or quote unquote factorize, 1 minus 4, 3, 3 and 1. So that's going to be u minus 3. U minus 1 is equal to 0. Therefore, tan alpha minus 3, tan alpha minus 1. And we get two values. Tan alpha is equal to 3, and tan alpha is equal to 1. Alright, let's quickly read part C and what part C was asking us for. Find the greatest possible height in meters of the ball above the ground as the ball moves from O to A. So essentially what's asking you is, what is this point here? Okay, what is that? What is the highest point? And essentially how you can work that out is when your final velocity is equal to 0. Because what happens is, as your velocity is increasing here, let's say this is 10, this is 12, and again it begins here to decrease. Let's say 10, 12, 10, 4, 3, and then here it will be 0, and then your velocity will start to decrease even, and it will go more and more negative because it's going downwards. Yes, your speed increases, but your velocity will continue to decrease. So at that point, your final velocity has to be 0. So we can use that essentially. Now we can work out a value of sine with it. It says find the greatest possible height, and we've got essentially two angles or two values of tan, and we need to be careful here which one we should use. Okay, and I would actually recommend you actually try with both of them. Let's work out a value of sine, because let me bring this 2 back down so I don't have to keep scrolling back up. Okay, we're trying to work out the value of s here. So I'm going to clean this up. We don't really have a value of t. We don't really care about the t value. We have the initial speed. We have the final speed. And we also have acceleration. And we're trying to work out distance. Okay. Let's work out the value of sine for both of these. Well, we're using SOHCAHTOA. Using SOHCAHTOA, you can find that tan alpha is the same thing as opposite over adjacent. Okay, so tan alpha for 3, tan alpha for 3 means this is the same thing as 3 over 1, and this is the same thing as 1 over 1. We can do this and make a right angle triangle for both of them. Right, 90 degrees and 90 degrees. Okay, and I'm just going to call this here alpha. Therefore, this is going to be opposite over adjacent, opposite over adjacent. Let's work out what this hypotenuse is, because if we're trying to work out sine alpha, well, we need a hypotenuse. Okay, using some Pythagoras, you should find that this is going to be equal to root 10, and this is going to be equal to root 2. Therefore, to work out sine alpha, we do opposite over hypotenuse, which is going to be 3 over root 10 in this case, and this one here is going to be 1 over root 2, or just root 2 over 2, but I'll keep it as 1 over root 2 for now. Okay. Now what we do is essentially make an equation for working out our s value. Well, again, let's pull our formulas. Let me go back up somewhere here. Where's it gone? Quite far up, right? What's here? Okay, we're going to be using one of these formulas to work out our s value. Well, we've got s, we've got u, we've got v, and we've got a. So we're going to be using v squared equals u squared plus 2as. So we got v squared is equal to u squared plus 2as. Therefore, I'm going to keep it in terms of sine for now, and I'm just going to sub into the calculator later on, just to make it a bit more, easier to work out. V squared is going to be 0. U squared is going to be 28 sine alpha all squared, plus 2 times by minus g times by s. I'm going to rearrange this for s, and you can probably already substitute stuff in if you really want. You can even substitute this in, but I'll show you why I'm doing this. It's just a lot more easier in my opinion. Let me clean things up real quick. This is going to be like so, is equal to 0. I'm going to move this to the right hand side, so this becomes 28 sine alpha all squared is equal to 2gs. I'm going to divide by 2g. 28 sine alpha all squared over 2g is equal to my distance. Now at the moment I have two values for sine alpha, which is 1 over root 2 and 3 over root 10. I'm going to try both of them. Okay, so what I'm going to type into my CG50, and you can kind of do this with your other calculator as well. So I'm going to type in 3 over root 10 first. This is just me being lazy, to be honest. You can type it manually, but it's going to be 28. 1 second. 28. I don't know why there's like a little box around there. I'm going to 28 answer squared. The reason why I've chosen answer is because this is my whole value of sine alpha. Okay, over 2g. Okay, so my first answer I get is 36. Okay, s equals 36. My other answer, if I switch 3 over root 10 to 1 over root 2, that's going to give me 20. Okay, but as you can see, our maximum height definitely cannot be 20 because it already goes to 20. Therefore, your maximum height must be 36 meters. Okay, so you can put a little statement. Nope, sine alpha cannot be 1 over root 2. Sine alpha is equal to 3 over root 10. Therefore, max height is equal to 36 meters. Okay, that's 4 marks for that. Alright, next part of the question. Part D, state one other limitation of the model. If you ever have projectiles, this is something that I always put. Okay, wind effect. This always gets you marks. Sometimes very, very rarely you might not. But you can talk about other things like spin of the ball. You can potentially talk about what else can we talk about? Like the dimensions of the ball itself. Maybe it's not fully spherical. Maybe it's what else? I'm trying to think off the top of my head. That's what's coming to my mind right now. But I think studying the mark scheme for these will definitely help you a lot. But in my opinion, wind effect is the best one. That's something that I always put. All right. Part 6. Moments. So you can put a little statement. Nope. Sine alpha cannot be 1 over root 2. Sine alpha is equal to 3 over root 10. Therefore, max height is equal to 36 meters. Okay, that's 4 marks for that. All right. Next part of the question. Part D, state one other limitation of the model. If you ever have projectiles, this is something that I always put. Okay, wind effect. This always gets you marks. Sometimes, very, very rarely, you might not. But you can talk about other things like spin of the ball. You can potentially talk about what else can we talk about? Like the dimensions of the ball itself. Maybe it's not fully spherical. Maybe it's what else? I'm trying to think off the top of my head. That's what's coming to my mind right now. But I think studying the mark scheme for these will definitely help you a lot. But in my opinion, wind effect is the best one. That's something that I always put. All right. So before we start question 6, I actually want to. Well, we know that this is the moments question just by looking at this, right? But let's continue to read this first part. But before you even start the question itself, I'm going to do some annotations. Okay, a rod AB has mass m and length 2a. The rod has its end on A on a rough horizontal ground, and its end B against a smooth vertical wall. The rod makes an angle theta with the ground, and the rod is at rest in limiting equilibrium. Do we know if it's uniform? And it does say actually the rod is being uniform. All right, let's actually answer part A just because it's part 1. State the direction left or right on figure 3 above of the frictional force acting on the rod at A. So essentially, if the rod is trying, well, if it's sitting on the ground right now, what it's going to do is try to slip down the wall, right? The rod is trying to slip down the wall, and that means the rod will try to move forward at the same time. Okay, imagine you're leaning on a wall. There's a guy that's leaning on the wall. Okay, what will happen is he'll end up essentially trying. Okay, that is that did not mean that. He will try to essentially end up like this. Okay, so the rod is essentially trying to move left. So if the rod is trying to move left, that means that the frictional force has to be going towards right. Okay, cool. Well, that's part A. Well, to the right. That pen is really fat. I don't like that. Right. All right. Let's start to annotate some stuff. Okay. We know friction is going towards right. We'll use that. I'm gonna call this RA, and I know in the mark scheme and stuff is they call it in different letters. I'm gonna call this RA and RB. So there's gonna be reaction force off the floor, and there's also gonna be reaction force off the wall. Now, because this is a uniform rod, and we know the mass is m, okay, there's actually going to be a downwards force directly in the middle of the rod, which is going to be mg. However, in moments, you're going to be working with perpendicular forces, and there's not one way of annotating this, by the way. In the mark schemes, there are multiple ways of doing this. In my opinion, this is the best way of doing this. Okay, so I'm actually going to keep this in, let's keep this in black for now, actually. Okay, and I'm going to show you the proof behind this, but you do not need to do this, actually. You can just directly do the annotation. Okay, so if I have a downwards force of mg, and I'll show you why I've kind of drawn this in a longer way. Okay, I want to work out what the perpendicular force will be, which is this, and I'm going to do this in orange. Okay, now you can see that this angle here would be 90, and you can see that this here is a triangle. And therefore, this angle here will be 90 minus theta. Well, we know that this angle here, this orange force, is perpendicular, so therefore this must be 90 degrees. Therefore, this angle here must be theta, right? And if I just make this a triangle, if I just connect these two together, let's just say this is a right angle triangle. Well, now I have a right angle triangle with mg as my hypotenuse. I have an angle theta here, and I want to work out this orange force, and actually we can work out this purple force here as well, which is going to be essentially this one down here, right? So the orange force using some SOHCAHTOA, well, SOHCAHTOA, this purple force is going to be opposite, and the orange force is going to be adjacent. Therefore, this purple force, if we have sine of theta is equal to, or even, yes, yeah, so sine of theta is equal to opposite of a hypotenuse, where we have the hypotenuse as mg. Therefore, this is going to be mg sine theta, and the orange force is going to be mg cos theta. Okay, and you can actually learn these themselves. You don't actually need to show the proof for this. So you can actually just write down that this orange force is mg cos theta, and we do have that downwards force as well, like so. Okay, now to make this, you need, now to make this, the key thing you need is essentially to extend this force to a hypotenuse, basically. Okay, you're trying to make a right angle, and essentially what you're trying to make a right angle of is making this original force, this original black force, your hypotenuse. You're essentially trying to make it your hypotenuse, and once you've done that, you can essentially access its vertical components and its horizontal components very, very easily. Okay, and that's exactly kind of what I want you to do when you're trying to work out the horizontal and vertical components, or I should say the perpendicular and parallel components for RA and RB. Okay, so we've got mg cos theta now. We don't actually need mg sine theta. Reason being, it's just a downwards force. Okay, it's not actually a particle or anything. It's the actual weight of the rod, so we don't need an mg sine theta here. Okay, great. Technically there is, but because it's going in the same direction of the rod, we don't actually need to consider it at all. It's just there. We don't need it. All right. Next thing. I'm also going to work out the perpendicular force for RA, and I'm also going to work out the perpendicular force for RB. We probably don't even need RA. RA is 1, but it can come in handy. Okay, so exactly the same thing. What I'm going to do is extend along my main force, which is going to be RA. Okay, and then I'm just going to connect these two together. Just connect the two lines together. You don't want to make the orange one too long. Okay, just make it to a certain extent where you can just connect them together and just call this angle 90 degrees. Okay, usually the small angle that you see here will be your theta. Okay, but we can always work it out just to prove it. Well, if we know that this is perpendicular to 90 degrees, that means this has to be 90 minus theta. But we also know that this orange force here needs to be perpendicular, like so. Therefore, this angle here must be 90, which makes this angle theta. Okay, you can try doing an assumption. Usually you will be right, but that's the actual proof behind it. Okay, so again, we don't need that green force, to be honest. We're really more interested in this orange force, but I'm just going to bring this whole triangle down like so. Okay, so I have RA here, I have theta here, and I'm more interested in this bottom angle here. Well, this is your opposite and this is your adjacent. So if it's your adjacent, you're going to be using cos. So this is going to be RA cos alpha. Okay, and we've got that force now. Oh no, my OneNote crashed. Oh, there we go, it's back. Too much writing. It does that sometimes. Anyways, where were we? So this orange force here is going to be RA cos theta. I can draw. I want you guys to try the same thing for RB. Okay, work out the angle and find out if this is a sine or if it's a cos. All right, let's see what this is going to be. First things first, what I'm going to do is make RB my hypotenuse. So I'm just going to extend this along quite a bit. Okay, I'm more interested in this force here. And then I'm just going to connect these two together, and this is going to make my 90-degree angle. But I need to work out what my my theta is, or where my theta is. I'm just going to assume it's probably there, but let's try to prove it. Well, with alternate angles, this is theta. Okay, so I know that this is 90 degrees because my orange force is perpendicular. Therefore, this angle here is going to be 90 minus theta. Okay, so my assumption was kind of wrong, but this means that this angle here must be theta. Okay, cool. what I'm going to now do is kind of flip this triangle over, so I end up with this force here, and this purple force here is going to be my RB, and that is my hypotenuse. And then what I'm more interested in is in this bottom force, and my angle is going to be on the top. Okay, you can see that if I flip this around, this does match. Essentially kind of matches if I flip this around like so. There we go. You can see that matches. Okay, cool. So that's RB. And then this angle is going to be my 90 degrees. All right, perfect. So I want to work out my orange force here. Well, you can see this is the opposite. Therefore, this is going to be RB sine theta. Perfect. Now we've got our perpendicular forces. RB sine theta. Now we can just apply moments and everything is just going to match. You're going to watch how easy this is going to be now. Let's see if we need any more information. This was mg. Okay. 3 things we need to know. Okay. First, our vertical forces equal. 3 things we need to know. Vertical forces, you're up, it's going to equal to your down forces. Your horizontal forces, your left is equal to your right forces. Okay, and then we're also going to do moments around the forces, around the point which has the most forces, which is probably going to be A most of the time. Okay, you can also work out the perpendicular for friction, and I'm actually going to work it out just for the sake of practice after we've done the question. So if you want to try that just for practice, work it out for friction, try to see what this orange force will be for friction. Okay, because it takes a bit of a time to get used to if you haven't used this method before. Okay, but let's do the moments question itself. Right. So what we have essentially is I'm going to do up equals down first. I'm going to get rid of all these triangles because we don't really need them. Okay, up equals down. So my downwards force is going to be mg, and my upwards force in this case is going to be Ra. Perfect. Well, we've already got that out of the way. Let's keep going. My horizontal forces, my friction is equal to my Rb. Therefore, since my friction formula is equal to mu r, in this case my reaction force is just Ra. Therefore, mu Ra is equal to Rb. Okay, that is my next equation. All right. Lastly, let's do moments about A. Well, moments about A, that's going to be, well, the center distance here now is very, very important which force you pick. And that's why I think that picking the perpendicular forces really, really helps. Because you can just solely focus on them. Well, this is A away from the start because it's right in the middle, it's uniform. So it's going to be A times by mg cos theta. And we have to think about what is our clockwise motion and what is our anti-clockwise motion. So what you can pretend to do is put your finger down on the moment point, so in this case A, and then imagine yourself pulling this from this area here. Okay, so if you put your finger on A and you pull, where is your rod going to turn towards? Well, it's going to be turning in this direction, therefore that is clockwise. Okay, do that the same thing for the other force. So again, put your finger on A and then imagine yourself pulling from the RB sine theta, so a perpendicular force we're focusing on. Okay, and you'll see that it'll be going anti-clockwise. Okay, so that means that this is going to be anti-clockwise moment, and it's going to be a clockwise moment relative to A. All right, perfect. And that equals to, therefore, our distance, which is 2A because right to the end, 2A RB sine theta. Perfect. I'm going to cancel out the a, so this gives me mg cos theta is equal to 2rb sine theta. All right. Well, I know that rb is the same thing as mu mg even, because I know ra is equal to mg. So I'm going to rewrite this equation here as the following. Mg cos theta is equal to 2 mu mg sine theta I'm just going to try to simplify this as much as I can, to be honest. And let's continue to simplify. Well, actually, before we even do that, I'm going to even stop and just look at part B. I'm kind of interested in this because the question is saying, okay, the magnitude of the normal reaction of the wall on the rod at B is S. So we said that S is RB, which is fine. In an initial model, the model is being uniform, fine. By taking moments about A, show that S is equal to this. So let's go ahead and rearrange for RB first, and then we'll worry about substituting this in. Okay. So let me just quickly rearrange for RB. So what we end up with essentially is a half mg cos theta divided by sine theta, and we know that cos theta over sine theta is the same thing as cot theta. Okay, that was a very, very easy 3 marks in my opinion, just because we annotated in this perpendicular way. All right. Now it's told us that the coefficient of the ground is mu. Given that tan theta is 3/4, find the value of mu. Okay, so if they ever give you a value of tan theta, okay, well, this is the first thing that you should do. Write down SOHCAHTOA. This is my habit, but you just need TOA. Tan is the same thing as opposite of adjacent, and you should try to use this method. Never ever do inverse tan on your calculator, just because sometimes what happens is, even though you may get some nice answers, sometimes they will give you numbers where you don't, like root 12 or root 19 or something like that. Okay, so draw yourself a right angle triangle. Okay, make an angle like so. In the relative to the angle, this is going to be opposite over adjacent, so that's going to be 3 and 4 there. And using some Pythagoras or some knowledge of your Pythagoras triangles, you get that 5 is going to be a hypotenuse. Therefore, sine alpha is going to be opposite of hypotenuse, which is 3/5, and cos alpha is going to be 4/5. Okay. Let's continue on. What I'm going to do is now substitute in my RB just to see what happens with this. Therefore, if I know that RB is equal to this, and I know that at the beginning we know that RB is equal to mu mg with this part, I get that mu mg is equal to a half mg cot theta. I can cancel out the mg's. Mu is equal to a half cot theta. Well, cot theta is the same thing as cos theta over sine theta. And we worked out the cos theta and sine theta. So that's going to be essentially a half times by 4/5 over 3/5. Let me just double check that. Yep. This is the same thing as a half times by 4/3. And that's the same thing as 2/3. Mu is going to equal to 2/3. Perfect. Easy 5 marks in my opinion. That is beautiful 5 marks. And that just again comes down to your really, really good annotation. Part D. Find in terms of mg the magnitude of the resultant force acting on A. So we're trying to work out essentially what is Ra in terms of mg. Well, we worked out mu. We worked out mu is 2/3. Cool. Let me just double check that even. The magnitude of the resultant force acting on the rod at A. Okay, so I take that back actually. What we're trying to do is essentially work out this force even. So essentially we have a force going upwards, which is the reactional force. We also have a frictional force going in the right direction, and essentially what we're going to do is we're going to do Pythagoras on that, and that's essentially our resultant force on the rod itself. Okay, so what we have is we're going to do Ra squared plus our frictional squared and then square root that. That's going to be the magnitude of that using Pythagoras on that. Okay, but we know Ra is already mg. Okay, so this is going to be mg squared or mg squared like that. Friction, well, we worked out friction as mu mg. Well, that's just going to be plus 2/3 mg all squared, and then we square root that. Well, this is going to be the same thing as square root of m squared g squared plus 4/9. That's a weird 9. 4/9 m squared g squared. That gives you, if we add that together, 13/9 m squared g squared. And I'm actually going to put this as brackets like so. And this is going to be the same thing as square root of 13/9 times by mg, because this part gets square rooted as well. So I'm just going to write this as mg outside the square root. And then if I decide to simplify this a bit more, this is going to be root 13/3 mg. Okay, I think this is a nice way of writing it. looks clean, and that's easy again, 3 marks. In a new model, the rod is modeled as being non-uniform, with the center of mass being closer to B than it is to A. A new value of S is calculated using this model with tan theta is equal to 3/4. State whether the new value for S, so in this case RB, is larger, smaller, or equal to that S would take using the initial model. Okay, essentially what it's saying is that we might have a center of mass here, and the best way to think about it is essentially just pick a number, or let's say that instead of A, now this is going to be 1.5A. Okay, and let's check. Let's see what happens in terms of that RB. Okay, so instead of having AMG cos theta, let's say we have 3 over 2A mg cos theta is equal to 2A RB sine theta. Okay, I'm just going to rearrange this, right? That cancels out. This becomes 3 over 4 mg cot theta is equal to RB. In comparison to before, where we had a half mg cot theta, and this is now 3/4 mg cot theta, well, the value of S is talking about RB here. What's happened? Well, you can see it's gotten larger. Okay, so why has that happened? Is because essentially your moment about from A has increased. Okay, and you even doing this calculation is completely valid actually as well. But again, you should probably put a statement. Moment is larger from A as more distance. Therefore, RB is larger. Or S is larger. Okay. Doesn't really matter, it's just a variable. Cool. 4 marks on that. Beautiful question. Really, really nice. The end bit of the video, if you did practice the component for friction, which is in this direction here, well, let's do it now. Okay, well, we're trying to make the part that we already know, the hypotenuse, which is going to be friction, and we're going to try to make this right angle, like so. Okay, now right angle will probably be here. We need to work out this angle, but since we know that this is going to be perpendicular, well, that makes this angle here 90 minus theta, which makes this angle theta. So now I have a triangle like so, where this angle on the top is theta, this is 90 degrees, and this part is friction. And what I'm interested in is this part here. Well, this is opposite. Well, if it's opposite, then this is going to be FR sine of theta, like so. And that's it.